यस हम ही है गुरुकुल हमारा।
Hello students, welcome to the class of Circuit Theory and Network. This video is made for the students of Computer Science Engineering of 3rd SEM. I'm Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this video, we have discussed the series resonance, and it consists of resonance, classification of resonance, series resonance, properties, variation of circuit parameter with the frequency variation, and the Q factor, bandwidth, and examples, and the references. So let's start with resonance. Now, what is a resonance? Resonance is a very important property of a reactive AC circuit employed in a variety of applications. And any system having at least a pair of complex conjugate poles has a natural frequency of oscillation. If the frequency of the system driving force coincides with the natural frequency of oscillation, the system resonates and the system response becomes maximum. This phenomenon is known as the resonance, and the frequency at which this phenomenon occurs is known as the resonant frequency. In an electrical system, the resonance occurs when the system contains at least one inductor and one capacitor. And under resonance, the circuit is purely resistive in nature and is termed as a resonant circuit or the tuned circuit. And designing of any electrical, mechanical or civil structure, the effect of resonance must be taken into consideration to avoid the system to be damaged due to the large system oscillations. Now, the electrical resonance can be classified into two categories. One is series resonance, which is also known as the voltage resonance, and another one is the parallel resonance or the anti-resonance, and it is also known as the current resonance. And in this video, we will consider the series resonance only. Now, for the series resonance, we have to consider a series RLC circuit, which is also known as the voltage resonance. And in series RLC circuit, the RL and C are connected with a variable frequency supply V, and the current I is flowing through the circuit. The drop across the resistance is VR, the drop across the inductor is VL, and drop across capacitance is PC. Now, for this series RLC circuit, the total impedance equal to R plus J into XL minus XC, where XL is the inductive reactance and XC is the capacitive reactance. And XL is denoted as 2 pi FL or omega L, whereas XC is 1 by 2 pi FC or the omega C. Now, the net reactance is the absolute value of the difference between two reactances, that is, the sign of the result is to be considered as positive, no matter which one of these two reactances are greater. That's why we are considering the mod of XL minus XC, that is, we are considering absolute value. Now, from these equations, XL equal to 2 pi FL and X equal to 1 by 2 pi FC, we can say that both reactances are frequently dependent, and the frequency and the XL, that is the inductive reactance, is directly proportional with the frequency, whereas the capacitive reactance is inversely proportional to the frequency. And at the frequency of the supplies increase, XL increases and XC decreases. At the low frequency, the XC is infinitely large, and as the frequency increases, XC starts to decrease but never goes to 0. Similarly, for the low frequency, XL starts from 0 and increases linearly with the frequency. Now, at the resonating frequency, this imaginary term becomes 0, so the total impedance becomes the total resistance. and XL is equal to XC. So if we compare this XL is equal to XC, that means 2 pi FL equal to 1 by 2 pi FC. Then we can find out the resonating frequency F equal to 1 by 2 pi root over of LC. And the current through this circuit is V divided by root over of R square plus XL minus XC whole square. And at resonating condition, this XL becomes XC, so this difference becomes 0. So I becomes V divided by R. So at resonance, it is working as a purely resistive circuit. So here, these are the phasors of RLC and the RLC circuit. So for the pure resistance, the voltage and current are in the same phase. For the inductance, the voltage leads the current by 90 degrees, whereas in capacitance, the voltage lags the current by 90 degrees. And if we consider the series RLC circuit and considering that VL is much more greater than VC, because here VL and VC are in opposition, that means 180 degrees phase difference is there. And if we consider VL is greater than VC, then VL minus VC is in this side, and the total supply voltage V is the phasor sum of this VR and VL minus VC. Next is the properties of the resonance. So in resonating condition, the applied voltage and the resulting current are in same phase, which means that the power factor of the RLC series circuit in resonating condition is unique. That means same as the purely resistive circuit, as it is acting as a purely resistive circuit. And the net reactance is 0 at resonance, and impedance does have the resistive part only. The current in the circuit is maximum, and that is equal to V divided by R. And at resonance, the line current is in series. RLC circuit is maximum, and it can accept the maximum current, and hence it is called the acceptor circuit. At resonance, the circuit has the minimum impedance as well as the maximum admittance, and the resonating frequency becomes 1 by 2 pi to the power of LC. Now, in resonating conditions, VL and VC will in same magnitude, and both will be cancelled out. So the only voltage is equal to VR, and it is acting as a purely resistive circuit. Next is the variation of circuit parameters with the frequency. So XL is the inductive reactance, and that is equal to 2 pi Fn or omega L. And if we consider this, compare this with equation y is equal to mx, then it becomes the equation of straight line, and it is starts from 0 and starts to increase when the frequency is increasing, as the both inductive reactance and capacitance reactance are depending on the frequency. So frequency is varying in the x-axis, and next we are plotting the XL, and XL curve is a straight line, whereas if we consider the curve of XC, it is a general equation of the hyperbola, whereas the frequency is a variable, the constant becomes 1 by 2 pi C, and it looks like this hyperbolic equation. And at the resonating condition, that means in this frequency, the XL value is equal to the XC value, and in this condition, the impedance is minimum. Now, the frequency less than this FR, that is the resonating frequency, the XC value is much more greater than the XC. So, in this area, the capacitor, it is acts as a capacitive circuit, whereas the above the resonating frequency, the XC value is much more less than the XL. So, XL is greater than XC, and above this frequency, it is act as a inductive circuit, whereas at the resonance it is acting as the purely resistive circuit. And next is the current response curve, and here the in x-axis omega is varying and I is in the y-axis, and at resonating frequency the current is the maximum, and it is denoted by Vm divided by R. So next we are considering two another frequencies, that is omega 1 and omega 2, and these are identified in such a way such that the current in this portion is the total maximum current is Im, then it becomes Im by root 2, or it can be written as 0.707 Vm divided by R. So both the cases the current is Imax by root 2 and the voltage is Vmax by root 2, so the power becomes RMS power, that is equal to P divided by root 2 into root 2, that is P divided by 2, total half of the maximum power. And hence these points are called the half power points. Whereas if this one is the lower half power frequency and this is the upper half power frequency. And this curve is asymptotic in nature, and in the frequency lower than the resonating frequency, the circuit behaves like the capacitive circuit, and the frequency higher than the resonating frequency, it behaves like the inductive circuit. Next is the variation of voltage with the frequency. Now, when frequency is varying in x-axis, then we can see from this graph that the voltage across capacitance denoted by the solid line and voltage across the inductance that is denoted by the dotted lines are equal but in opposition. That means they have opposite phase and both can be cancelled out. And each of them is much greater than the supply voltage. Such condition is referred as the resonance, and it has an effect that is extremely important in the communication systems. For an example, we can consider the radio. Next is the quality factor or the Q factor of a series RLC circuit. Now, Q factor or the quality factor of a series RLC circuit is defined as the ratio of the voltage across the inductor or the voltage across the capacitor to the applied voltage, and it is also called the voltage magnification in the circuit as resonance. So now Q can be written as PL by V. PL is the inductor voltage and V is the supply voltage, and that is equal to Vc by V. So when we are considering VL by V, VL is equal to I into XL, whereas V is equal to I into R, and it can be written as XL divided by R. XL is also omega into L divided by R, and from this we can consider that root over of L by R into root over of C. And in case of Vc, so Q equal to Vc by V, in the same way Vc is equal to I into Xc by I into R, I can be cancelled out, so it becomes Xc divided by R, that is equal to 1 by R into omega into C. Or Vc is equal to Q into V. From this equation we can find out the Vc is equal to root over of L by R into root over of C. So from these equations we can say that the voltage across the inductor that is equal to voltage across the capacitor. And in both the cases, the Q factor is equal to root over of L by R into root over of C. Next is the bandwidth. So again, we are considering the current response curve. And in current response curve, at the frequency, resonating frequency, the value of the current is Vm by R, whereas in between this F1 and F2, the value is I by root 2. Or that can be written as 0.707 Vm divided by R. Now, the frequency band within these limits of the lower, F1 is considered here as the lower and F2 is considered as the upper half power frequency, is called the bandwidth of the resonant circuit, and the response at this resonant circuit within this bandwidth is assumed to be flat. So, in case of F1 frequency, the I of F1 and in case of F2 both have the same current, that is equal to Vm divided by root 2 into R, that is equal to Vm by Z, or equating these two we can say Z is equal to root 2 into R. But we know that Z is equal to root over R square plus XL minus XC whole square. So equating these two equations we can say R is equal to XL plus minus XL minus XC, whereas this plus minus indicates the predominance of either XL or XC depending on lower or upper frequency range. Now we are considering that at F1 frequency the R is negative and at F2 the R is positive. So we can say the R is equal to omega 2L minus 1 by omega 2C, and minus of R is equal to 1 by omega 1L minus 1 by omega 1C. Now if we add this equation 5 with equation 6, then we can find out that omega 1 into omega 2 that is equal to 1 by L2, and that is equal to omega square. And if we subtract this equation 6 from equation 5 and then divide both sides by L, then we can find out minus omega 1 plus omega 2 is equal to R by L. Now we know that omega L by R, that is the Q factor, or omega by Q is omega 2 minus omega 1. Whereas we can say that omega q is equal to omega by omega 2 minus omega 1. That is omega. Omega is 2 pi into f and omega 2 is 2 pi into f2 minus 2 pi f of 1. So 2 pi can be cancelled out in both numerator and denominator. So it becomes the resonant frequency by the bandwidth. So in this way we can relate the Q factor with the bandwidth, and the Q factor is the ratio of resonant frequency by bandwidth. And using this equation, omega 1 into omega 2, that is equal to 1 by LC, that is equal to omega square. So we can say that omega is the geometric mean, omega is the resonating frequency, which is the geometric mean of the two half power frequencies. So let us take an example. So a circuit is given which has the resistance of 4 ohm and inductance is 0.5 Henry. Variable capacitance is series and it is connected across 100 volt 50 Hz supply. We need to calculate the capacitance at the resonating condition and the voltage across inductance and capacitance, that is VL and DC, and the Q factor of the circuit. So for the first one, we know that if XL is equal to 1 by XC, that is X is equal to 1 by 2 pi FC and XL equal to 2 pi FL. So using these two equations, we can find out the value of C, that is equal to 1 by 2 pi FR whole square into L, and we can obtain the value that is equal to 20.3 microfarad. Next is the voltage across inductance and capacitance at resonating condition, and we know at resonating condition VL is equal to VC. So the VL is equal to, using the same formula, VL is equal to becomes 3930, and as VL is equal to VC, so VC also 3930 volt. Or we can use the formula of VC is equal to I into XC also, and then I by XC. In both way, we can find out the voltage of capacitance and the inductance. And for the Q factor of the circuit, we can use the formula Q equal to 2 pi F into L by R. So we can find out the value 39.3, and as the Q factor is the ratio of two voltages, there is no unit. And let us consider another example. And here bandwidth of a series resonance circuit is given, where resonating frequency is given as 6000 Hz, and we need to find out the value of the quality factor. And resistance value is given as the 10 ohm, then we need to find out the inductive reactance of resonance and the inductance and capacitance of the circuit. Now we know the bandwidth of a circuit, RLC series circuit, is given as resonating frequency by Q factor, or the Q factor is the ratio of resonating frequency by bandwidth. So bandwidth is given as the 500 and the resonating frequency is 6000. So ratio of these two becomes 12. So the Q factor of the circuit is 12, and the value of inductive reactance, that is XL is equal to 2 pi FL and equal to Q into R. So equating these two, we can find out the value of L, that is 3.18 millihenry. And at resonating condition, XL is equal to XC, so XC also becomes 120 ohm, and XC is equal to 1 by 2 pi FC. From this equation, we can say C is equal to 1 by 2 pi F into XC. So putting the values, we can find out the value of C, that is equal to 0.22 microfarad. So in this lecture, we have considered the series resonance, the properties of the series resonance, and the variation of resistance, inductance, and capacitive reactance with the frequency, the variation of current and impedance in a series resonating circuit, the bandwidth, the Q factor, the relationship between the bandwidth and Q factor, and some numerical problems. And in the next video, we will consider the parallel resonance. And these are the references. Thank you.
Hope after this video lecture you have a clear idea about today's topic. Now we will go through some questions answer session in the context of this video lecture. Now you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.